Good afternoon. I'm Mr. H. Thank you for joining me for this video. We're looking here at more partial fraction decomposition, but we're looking at now another complexity of these forms. Look right here, account for all combination of linear factors. What does that mean? You know, we've looked at the simple cases, we've looked at the non-reducible linear factors, and now we're looking here at the fact that you have to account for all combination of linear factors. Consider this. You have a certain numerator here, whatever it might be, under which you've taken the denominator polynomial and you factored it out, and the result of your factor has given you something which looks like this. Let me make this ax cubed. You've determined this to be your factors from your polynomial. This could have been very well your denominator, which when you factored it out you got this because you isolated x cubed. Now, what does it mean when you have to account for all combinations of linear factors? This is what it means. At first glance, you're thinking and you're seeing you have two items here, therefore you must have two items here. Something like this, an x cubed and x plus 1, but that would be wrong. The reason why it would be wrong is because you're not accounting for all combinations of linear factors. You're looking here at 1, but then you have to break this down into all the varieties of combinations. You have x squared, you have x cubed. These are the varieties of linear factors which fall right in here, because this is really an x times an x times an x, but here you have an x, you have an x squared, and you have an x cubed. When you look at this way, now you have 1, 2, 3, 4 linear factors. You have a over x plus b over x squared plus c over x cubed plus d over x1. That is exactly what your template becomes versus that. This right here is wrong, this right here is right. This is what you are thinking about when you have to account for all, because these are all the combinations of x cubed. X cubed is made up of x1, x squared, x3. So this is the peculiarity you need to keep in mind when you have a factor which looks like this in the denominator. So why don't we look at a question like that and utilizing exactly what we have seen. We'll have here x minus 1 or x cubed plus x to the fourth, and it will generate a template of that form. So let's look at it. Start with the numerator, keep it as is, look at the denominator and factor it out. You have x cubed and then you have x plus 1. This will give you x to the fourth, that'll give you your x cubed. It doesn't matter, 1 plus x, x plus 1, it's all the same. Now you're looking at a denominator which is made up of x times an x times an x times an x plus 1. You have a x minus 1 here. You're looking at all the varieties of linear factors. You have an x, you have an x squared, you have an x cubed, and then you have a x plus 1, into which you will put a, b, c, d. All of this right here will equal here in the numerator x minus 1 plus a bunch of placeholders. So now you see we have that. What's a good common denominator here? It will be x cubed times x plus 1. Now each of these individually has to be addressed. X goes in all of this, x squared and x plus 1 times. You see things will get complicated. This goes in here, how many times? It goes x and x plus 1 times. C goes in all of this, x plus 1 times, and d goes in all of that, x cubed times, and this must all equal in terms of this numerator 0x cubed, 0x squared plus x minus 1. You see I've accounted for all the varieties of items here, which you will see right over here when you open it up. But this is exactly what we're talking about, accounting for all the varieties and combinations of linear factors. You have to open this up. You'll have ax cubed plus ax squared. You have to open it up properly. Plus bx squared plus bx plus cx plus c plus dx cubed is equal to that. Let's look at our cubic terms. A and d. A plus d is equal to 0. Let's look at our quadratic terms. A squared bx squared. You have a plus b is equal to 0. Let's look at our linear terms. B plus c, right? B plus c is equal to 1. And then our constants are basically only 1. C is equal to minus 1. This is easy. You know c is equal to minus 1, therefore what must this be equal to? B must be equal to 2. You know b is equal to 2, therefore a must be equal to what? It must be minus 2, right? Minus 2 plus 2 will give you that 0. If a is equal to minus 2, d must be equal to 2. Now you have everything available. Put them in here. A is equal to minus 2, put that in. B is equal to 2, put it in. C is equal to minus 1, you can put that in as well, and D is equal to a 2, and we'll squeeze that in. So now what I want to do is erase this part here on the bottom and work it out in terms of a neat presentation for you with a finalized answer. It'll be minus 2 over x plus 2 over x squared minus 1 over x cubed plus 2 over x plus 1. This right here is your decomposed partial fraction of that rational function here. And there it is. Our second and last question is this: 2 plus x, or x plus 2 divided by x squared plus x to the fourth. And let's see how this one will play out. You can write x plus 2 here in the numerator, and you have to factor that out. You'll have x squared into 1 plus x squared. Now look at that. You have an irreducible linear factor, but you have a varieties of linear combinations that can come into play. X squared is made up of an x and an x, but in terms of combinations, you have x to the 1 and x squared. So what are you seeing? You're seeing 1, 2, 3 specific factors which will lead to a template of 3 items. Here you'll have a, here you'll have a b, but you have an irreducible linear factor. It's not a 1 minus x squared which could be reduced, it's a 1 plus. And here you must really put a cx plus d. You know, when you have an irreducible linear factor, you put an expression on the top. And you know you gotta do a common denominator here. It'll be x squared times 1 plus x squared. That's your common denominator. X goes in this, x and 1 plus x squared times, so you'll have a times x times 1 plus x squared. B goes in this common denominator, 1 plus x squared times, and then lastly cx plus d goes in that common denominator, x squared times. And you see all of that. You have to open it up. Opening it up can lead to a mistake, and you want to avoid that. You have to open it up. You have a ax plus ax cube, and then here you have a b plus bx square, and then there you have a cx cube plus dx square is equal to, you have an x plus 2, but you're seeing a square and cube, so you have to put 0x cube, 0x square plus x plus 2. Now look at all the cubic items here. You have in terms of their coefficients, you have a plus c. See, you have ax cube, cx cube, those are your cubic items, a, c, and a 0. A plus c equals 0. Look at the quadratic terms. You have a b and a d. B plus d is equal to 0. Look at the linear terms. You have ax, and that's about it. A is equal to this coefficient, which is 1, and lastly you have this single item constant, b is equal to 2. And you see it's easy, right? If a is equal to 1 right here, c must be equal to minus 1, because it would cancel out, give you a 0. If b is equal to 2, d must be equal to minus 2. Let's put the items right here. We have a 1, we have a 2, we have a minus 1, and we have a minus 2. We have to just plug those in right here, and we will do that. A is a 1, b is a 2, c is a minus 1, and d is a minus 2, and there you have it, minus x minus 2. But we should clean it up and present you a good answer, and I will right over here on the bottom in a good way. My final decomposed partial fractions are 1 over x plus 2 over x squared minus x. Now I have to put a plus 2 over here, 1 plus x squared, because when I put this minus out here, it will impact these and convert them both into minuses. And you see how we're looking at that, minus x minus 2, and that's exactly what you have. This right here is your decomposed partial fraction. This answer is good, or this right here in this format is fine. Either way is fine. But you see, now you have to look at all the varieties of linear combinations, and that's how you have to do these. Thank you for watching. Have a nice day.